Hello, everybody. I hope things are going well with you. And this is lesson number 16 in Math 100. Lesson 16 is about logarithmic scales. So this is the second section in the two-part series on chapter 6. So chapter 6 is just about exponential growth and logarithmic growth or logarithmic scales. And there's only 2 lessons. All right, so let's look at the second part of chapter 6, logarithmic scales. All right, lesson number 16. This is based on 6.2. And actually, I should say that 6.3 is also partially covered. Although I don't think I give you any homework, certainly you will not see any exam questions on 6.3. That's about the pH levels in chemistry, which is also a logarithmic scale. But mostly, this will be on 6.2. And the main example we'll handle is the earthquake magnitudes, otherwise known as the Richter scale. All right, so the main question is this: what is a logarithmic scale and how does it work? And it is sort of deceptive. It's not deceptive in the sense that somebody is trying to deceive you. But if you don't know enough about this, and by the way, it doesn't take you long to just understand this basic idea. But if you don't know that idea, then you may be misled to believe on certain things like the seriousness or the magnitudes of earthquakes. All right, so what can we say? What can we start with? All right, so we will be talking about earthquakes in this particular, but the first idea that I want to discuss is this idea of magnitudes, right? The magnitude 7 earthquake, for instance, is a phrase, but the word magnitude does not have to do with earthquakes, right? We talk about the magnitudes of things, quantities all the time, right? So what it does is magnitudes describe rough estimates. In our decimal system, you know, we use a decimal system. It's called base 10. The word deci means, 10 or 10th. So base 10 system is what we use. And based on how many digits a number has, we can describe magnitudes to describe large and small numbers. All right, so if somebody says how many students are taking a math course at College of the Canyons or something like that, what would you say? A couple of people? Probably more than 2 or 3, right? Or more than 10, more than 100. Okay. In fact, we have I don't know, we have like 150 sections every semester. And so we would say it's thousands, okay? Thousands of people are taking it. Now, does this 1,000 give you any specific number? No, it's just an estimate, okay? And so that's a way to describe this. How about the entire Dodger Stadium, right? If the entire stadium is full, right? How many fans are there? 3, 5,000? No, it's like 50,000, right? But if you don't know the exact numbers, you can say you can say thousands, but it's more than that, right? You can say tens of thousands. All right, so that's a phrase describing the magnitude of the number of people at a stadium like that. How many Americans pay taxes? Well, we have like 300 million Americans, but some of them are children, and some of them don't pay taxes. But you can safely say it's more than 1 million people. Okay, in fact, it's millions of people. No, it's even more than that. It's hundreds of millions of people. So these are just rough ways of describing like what magnitude, how many zeros can we expect. All right, so the exponent to that number 10 is called the order of magnitude. Now, oops, that's over here. All right, what is a million? 1 million, if you write this out, it's 1, 0, 0, 0, 0, 0, 0. So you have 6 zeros. So millions, we say the order of magnitude is 6. For billions, order of magnitudes will be 3 times more than that. All right, tens of thousands. So write down 10,000, and you see that there are 4 zeros. Okay, by the way, this is 10 to the 4th. And I should have said 1 million is 10 to the 6. And so this number, okay, the exponent, remember the exponent to 10, that's called the order of magnitudes. So for tens of thousands, this will be 4, right? And we can use these exponents. People have looked at these exponents and say, hey, that's actually useful, right? Because if you say the order of magnitude is 9, we know we're talking about billions. So why don't we use these exponents to describe how big things are when we have to deal with huge numbers or a huge range of numbers? So, and this was a great idea. And this is how this whole idea of logarithmic scales were born. We can use these exponents to describe roughly large numbers. All right, so here's an application that you see, and this is 6.2. And this is our main application, Richter scale for earthquake intensity. Let me explain how this works. Right. So when scientists, basically geologists and seismologists in particular, started to measure the intensity or the energy released by an earthquake, okay, and that's what causes an earthquake. It's a release of energy from inside the earth. All right. And so when they tried to describe the energy level, they found that there's a wide range of numbers. Okay. Now, how do you describe like a shake? You know, how do you describe the energy that causes the earth to go back and forth, right? Well, you have to have some reference number. And so they do, and they have decided on this reference number. We are going to call this mu naught. Actually, it's often called mu naught, but the Greek letters are hard to type. So I'm just going to write M0 or M naught, okay? And so what is this M naught? Okay, this is a constant, a certain constant level of energy. It is a shake that is so small that no human could notice it, but they use this very small level of energy released in an earthquake, which is unnoticeable by human, to be the reference number. And then they will say this particular earthquake had, say, 100,000 times this energy level. Okay, that's how they describe this. So you have to have a threshold number, a constant, and they have decided to establish this. I don't know how they measure this, but there is a fixed number here. All right, now I have collected some data on some recent earthquakes. All right, so El Segundo is close to the airport, right, close to LAX. All right, so on October 2nd of 2019, there was a small earthquake. All right, that small earthquake was caused by the energy released, again, in the interior of the earth. That was about 40 times, basically 39.81 times that threshold level M naught. Okay, and I say it's small because this number particular is a small number. All right, I actually live in Castaic, California, north of Santa Clarita, and on February 21st, okay, and again, I didn't notice this one, but there was an earthquake based in Castaic. Ooh, scary. After that, I did feel this one because I woke up in the middle of the night with a big thud, okay? But that had 3,162 times this M naught, which is the lowest magnitude, which is used for the reference number, okay? Now, of course, in Europe is not known to have lots of earthquakes, but in 1992, Holland, the Netherlands, observed a pretty major earthquake, which had the intensity 158,000 times mu naught or M naught. And of course, you remember, or some of you may remember, some of you may not, because you weren't alive yet. 1994, we had a huge earthquake centered around Northridge, in the middle of the San Fernando Valley, and that had over 5 million times the energy referred to as mu naught. Okay. In January 28th of 2020, Jamaica, Cuba, and some of you may remember this in the news. This was a big shock, and literally. And so that had 50.12 million times the energy level used as a reference. My home country of Japan had one of the biggest earthquakes on March 11th of 2011, the Tohoku Great Earthquake, and that had over 1.2 billion times that level. All right. So the point I will use the a logarithmic scale to make sense of this. But you notice here the numbers change in a range from like 0, well, 39, all the way to like 1.6 or 1.26 billion. Right. So the range is really, really big. Okay. So how do you describe all of these? And the idea was, let's use this this exponent to describe the level or the magnitude of the earthquake. How do you describe all of these? It's hard because these numbers range widely. That is the problem. Okay, so in order to make a better sense or to understand these numbers better, Richter decided to use a logarithmic scale to describe these levels of earthquakes, right? So we use the common logarithm. And by the way, we have many different functions called logarithms in mathematics. In fact, we can define infinitely many of these. But the common logarithm is the number that is based on 10. So the question is 10 to what number is that given number? Okay, so that number is called the logarithmic, or the log, the common log of this particular number. All right. So let me explain this in just a minute. 100 is 10 squared, right? I'm going to go to the bottom line here. 100 is 10 squared. That's 10 times 10. Okay. And so what we do is we write this. Log of 100 is 2. Now let's see if you can make sense. All right. I know that, I mean, if you go into intermediate algebra or college algebra or pre-calculus, you study this function extensively along with different bases, not just 10. But we are going to use base 10. That's called the common logarithm. And the log of 100 is 2 because 10 to the second power is 100. Okay. So this number answers the question, 10 to what number is this particular number given? All right, so log of 100 is 2 because 10 to the second power is 100. All right, so how about a million? Okay, million is 10 to the sixth power. It's 10 times 10 times 10 times 10 times 10 times 10. And so we write log of a million. Sorry, log of a million is, guess what? Is 6 because 10 to the 6th is 1 million. All right, so this basically logarithm is the exponent, okay? The value of log is the exponent to the number 10. So the question you're asking is 10 to what number is this particular number, million in this case. All right, so with that, I hope I will make it clear. The Northridge earthquake in 1994 had 5.012 million times the reference number, right? So the magnitude we call is, and you can look this up, the magnitude of the Northridge earthquake was 6.7. Right? What in the world does 6.7 mean? Well, 6.7 earthquake means it's a big quake. And that's absolutely true. But the reason this is called a 6.7 earthquake is because 10 to the 6.7 turns out to be, remember, 10 to the 6 is a million. 10 to the 6.7 turns out to be about 5.1012 million, which is exactly this number here. All right, so here's what they do. They measure the intensity that caused the intensity of the energy that caused the earthquake, or the intensity of the energy released by that earthquake. And then they take the common logarithm of it, which means, 10 to what power is this number. Okay, where this number means it's, this number times mu naught is the energy level released by the earthquake. And that number, the exponent, becomes your magnitude. All right, so you say that was a 6.7 earthquake because the intensity of the energy caused by the earthquake was about 5.012 million times mu naught. All right, the one in the Netherlands, that was a 158,000 times mu naught, okay, or I should say m naught. We want to look at that number, and you ask the question, 10 to what number is that? And the answer is 5.2. Oh, by the way, you wouldn't know this number unless you use a calculator. And the calculator, you use this LOG key. I think every calculator, scientific calculator has an LOG key. And also you have another key here, but this is called a natural log. This is log with the base E. Remember that number E, the mysterious number, which I say holds the world, the universe together. This turns out to be a much more important function in the world of mathematics and science and engineering and so on. Right? Because of the mysterious nature of this number, and this becomes even more important in calculus. If you are really worried about this, or if you are curious about this, you can read the book that I talked about, the story of a number. But this is what we use. All right, so this is log with base 10. And this is the one we are going to use. All right, so if you want to find out what the log of 5.012 million is, you put this and then put 5.012 times 10 to the 6, and you will get 6.7. If you put 158,000, and then if you put log of that, you'll find 5.2, right? And that means 10 to the 5.2 power is 158,000, right? Now, normally you never see this number, right? Because these numbers vary so much, it's really sort of not very useful. But these numbers are much easier to understand if you understand this correctly. And that's why it's called the logarithmic numbers. All right, so with that, I want you to maybe think about this as we go to the second part of this lesson and the second part of the video lecture.